I'm Kara Miller.
And I'm Rob Stoner.
And from the MIT Energy Initiative, this is What If It Works, a podcast looking at the energy solutions for climate change. Today, we're going to examine an energy source with huge potential to shape the future, but one that's not without some complications: hydrogen. And let's start with a little story about hydrogen and how its power can kind of creep up on you. The story takes place in the late 1980s in Mali in West Africa.
Okay, so the Mali story is really an interesting one. This well that was being done to find water, and they got down to about 100 meters. They didn't find water, but they noticed that there was wind blowing out of the well.
That's Brad Hager, a professor of Earth, Atmospheric, and Planetary Sciences at MIT. He's also the associate director of the Earth Resources Lab.
So, as usual, they sat down for a break to ponder the situation. The crew member lit up a cigarette, and kaboom! This big blue flame shoots out. He was burned. Fortunately, he recovered. And it continued to burn in this bright blue flame for several weeks. So they had to figure out how to cap the well. And, capping wells is a little bit tricky. And especially in Mali, they didn't have the expertise to do it. But it burned for several weeks, and finally they capped it.
So what was the importance of this big blue flame? Well, no one explored it for a while, Hager says. The well just sat there for 15 years.
And a local entrepreneur decided that he would invest in a lot of parts of the Mali economy, and he invested in a wildcat oil and gas company. And so they decided they'd find out what was in the well. They took a sample, and they found out it was 98% pure hydrogen.
Now, this was a pretty amazing find, but Hager says there just wasn't the infrastructure to transport the hydrogen.
The only thing they could figure out to do with it was to run a generator. So they got an old Ford motor and hooked it up to a generator. They now produce electricity for the local village because they can't go anywhere. This is very exciting. The equivalent amount of energy that's produced in this well is about 3 barrels of oil equivalent each day, which is about 120 gallons of gasoline. So you can think 120 gallons a day, you can run a pretty big generator for a village, but that's about all you can do. Plus, Mali is politically unstable. There have been 3 coups since 2012 when they did this, so no big company is going to go in there and try to produce this.
But the find points to hydrogen as a clean energy source of the future. So let's say we could get a lot more hydrogen out of the ground. How would that change things?
It would be huge. So right now, we are producing about 100 million tons of hydrogen annually to use primarily for fertilizer manufacture. So you want to make ammonium, you want to feed the world, you use fertilizer made substantially out of hydrogen. But going into the future, using hydrogen to make steel, for example, instead of using coke, would take away a tremendous amount of the CO2.
But here's the catch. You don't find such concentrated sources of hydrogen in very many places.
So we do now understand why it's there in Mali. And it's a very special circumstance. There is a trap, very much like the traps that hold natural gas accumulations. And in this case, the trap is made out of a layer of solidified magma. Underneath that magma, there is a layer of limestone that has a lot of pore space in it. And then deep in the earth, maybe 1 or 2 kilometers below that, there are some very old rocks, over 1 billion years old, that are full of iron. And there is a small amount of water that percolates through this iron-rich rock. And there's a chemical reaction that goes on that converts some of the minerals in this rock to a kind of rock called serpentinite, which is the same as asbestos. In doing that, it takes the water and strips off the oxygen and uses that to essentially rust the iron that's in the rock and leaves behind the hydrogen. So over some period of time, we don't know how long, that hydrogen has been moving up towards the surface and accumulating in this reservoir below this cap rock.
Brad, there's a lot of iron down there in the Earth's crust and a lot of water that circulates beneath it as well. That would imply that if this reaction is going on between those two things, there's an awful lot of hydrogen potentially available to us.
Yeah, that sounds great. But so first of all, the iron-rich
That
rocks.
sounds great. But okay, now the other shoe's going to drop.
Ouch.
Go right ahead.
Okay, so first of all, the iron-rich rocks are not that common in the Earth's crust. Most of it we think about, silicon and other rocks, but in the crust, there's not much iron. Underneath Mali, there is a formation which is over 1 billion years old called a greenstone belt. It's a place where two continents smashed together and left kind of a scar that's full of iron-rich rocks. The place where there are really a lot of iron-rich rocks that are coming up near the Earth's surface are at the extending plate boundaries at mid-ocean ridges. In terms of water, we have a lot of water at the surface, but at great depth, although there's often water, it's not often circulating very much. And so in order to run this reaction, we need a continuous supply of water. So what's special about Mali is that they're right at the same place where there's this greenstone belt. There are also some old fractures that apparently are open a little bit, and there's water circulating through it. So there's a local source in Mali, but we don't know how much is being produced there. All we know is that at least some of it is being trapped by this cap rock.
So let me compare this to oil, which, people kind of have a sense of. Did you say it's like 3 barrels of oil a day coming up, right?
Yep.
So if hydrogen is an excellent energy source, is like sort of one of the things that's going to happen, or maybe already happened, that people are going to look around, just sort of they realize that there was stuff in Texas, but there's also oil in the Dakotas, but there's also oil in the Permian Basin. Are they going to look around and be like, well, so where's the hydrogen? Can we go to Kansas and find it?
So that's the process that's just beginning. And it's very much like oil was in the 1800s. People are beginning to look around, and there's a lot of effort in doing this. The United States Geological Survey has a big program to try to identify hydrogen systems that are comparable to petroleum systems. So what you need some source rock. In this case, it's water percolating through iron-rich rocks. You need some cap rock. In Mali, it's basalt. Most places, it's shale. And you need a reservoir rock where the hydrogen will accumulate. So right now, what people are doing is focusing on where these potential source rocks might be. So, for example, in the United States, there's an old continental rift scar extending from Nebraska, Kansas, Iowa, Minnesota, Michigan. There's a structure called the Mid-Continental Rift, and people right now are targeting that to see if they can find hydrogen there.
So are you saying that in, the upper Midwest, we're looking potentially at the kind of, I guess, not gold rush exactly, but I mean, there have been times where people got really excited about different sorts of energy all around the country and obviously the world. Is that going to happen? And people are going to go there and be like, we can get hydrogen out of the ground. It's clean. It's a great source of energy. See if we can make a bunch of money here.
That's exactly what people are doing. And
Okay.
Both because they want to make a lot of money and because they want to save the world. So there is a huge amount of interest right now in the venture capital community. There's a guy named Bill Gates, who you might have heard of, who has dumped a substantial amount of money into a startup company called Breakthrough Energy, which is going big into hydrogen. And just to quote Gates, it could be gigantic or it could be a bust. But if it's really there, wow.
Well, also we're hearing the people are estimating the cost if they're going to produce it like they produce natural gas by drilling into a deposit and sort of extracting it. And I'm hearing numbers like less than $1 a kilogram.
Yeah, that's right. So people are anticipating even 50 cents a kilogram for these pre-existing hydrogen deposits. And I think that's an order of magnitude less than what it costs to produce it by hydrolysis.
So that's wild, though. I mean, what a situation.
That's huge.
Here we are trying to make
Yep.
hydrogen through all these complicated, energy-intensive means, and it might be beneath our feet at a cost we'll probably never achieve or may never achieve with these other techniques.
That's right. It might be really cheap and would be a big help in the energy transition. So there are a lot of, as I said, venture capital companies going after this. There are some startups. There's one right up the street here in Somerville, a startup called Eden Geopower. It was founded by 2 graduates of our department. But the notable thing is that there are no major hydrocarbon companies investing in this. They are all sitting on the sidelines with a wait-and-see attitude. And what they're worried about is that, yes, there'll be some anecdotal finds, but there won't be enough there to justify the costs of the infrastructure to produce it and to really make a big impact. So they're playing wait and see.
That's very interesting that you've got the big I mean, obviously, like Bill Gates is plenty rich enough to saying, like, as you say, like, it could be big or it could be nothing, but whatever, he's got the money to bet on it. But big companies would also have money to bet, but it sounds like, no, they don't.
They have not only money, but they have data and considerable knowledge.
You mean
of
about what's under the ground?
Down there. I mean, these companies have been drilling holes, some of them for 100 years or more, and gathering all kinds of seismic data. Doesn't that give them a big advantage, Brad?
Well, one would think with all these holes they're drilling in the ground, but the issue is they're drilling those holes to find oil and gas. And they're finding very little hydrogen in the holes that they've analyzed. So that points to a problem, and that is that it is difficult to accumulate hydrogen in the Earth for two reasons. One, you alluded to it being a very small and slippery element, so it tends to escape. But the other thing is that microbes, I'll call them bugs for my geophysical terminology, bugs love to eat methane. So the big methane seeps on the Earth are at mid-ocean ridges where the plates are spreading apart and they're bringing hot rock up to the surface. Those rocks are fractured, seawater is circulating through them, and there is a lot of hydrogen being produced. And if there are any of these microbes around, they will eat it pretty fast.
Do people I think it's like Michigan and Minnesota and Iowa under Lake Superior where some of this stuff is. Do people know that this gold, like that they are, like Texas Part 2? Do they know this is happening?
Something good's going to happen in Michigan.
Well, it was realized in 2012 that we could get hydrogen from the ground. Mm-hmm. In 2018, about these venture capital companies began to be put together, and they began running around scooping up leases in places like Iowa and Kansas. Anyway, around 2 years ago, there was a great outpouring of publicity in journals like Science and Nature talking about the potentials of hydrogen. So it's being picked up broadly in the press now, and everybody's excited about it.
So there's a gold rush going on, kind of, getting going.
Beginning of a gold rush.
And it's not just in the United States. I mean, I'm hearing about big discoveries in Eastern Europe, Africa for sure, maybe South America, Australia.
Yep.
It's all over the place. Is that what's going to happen? We're going to find this stuff and start producing it like natural gas?
Well, I think that we will find some of it. Australia is pretty far ahead, and new finds keep coming up. Albania, the Pyrenees of Spain. I mean, there are a lot of these places. As you mentioned, Bill Gates has a lot of money. He can bet on this. I don't have enough money to bet, but I can bet my time.
Would you say you have so little money that you have to bet?
I have so little. Yes. I desperately want to make a contribution to saving the climate. Earth scientists have this saying, we have multiple working hypotheses. Okay. And my working hypothesis is that in the very near future, we are going to run out of the hydrogen that is naturally accumulated, analogous to natural gas accumulations.
Because even if there's a high generation rate, it's leaking out all over the place much faster than natural gas would. Right. Bugs are eating it.
Bugs are eating it, and groundwater flow in continental interiors is pretty slow. So I don't think we're going to be able to keep up using this analog of the kind of conventional natural gas system. Yeah. So I think what would be the real breakthrough, and I think it's the breakthrough that we should bet on here at MIT, is answering the question: can we actively produce hydrogen in the same way that it's being actively produced at these mid-ocean ridge systems, where water is circulating through hot iron-rich rocks and reacting in real time and at high rates with the water and the rocks are reacting. Hydrogen is being generated, and it's coming up to the surface rapidly enough that there's more of it than the bugs can eat, and that it could be produced.
So it's being produced in kind of real time. This is not like old deposits, yep. Right? Kind of like there's deep water drilling, like you're down there in the water capturing it in real time.
Yes.
As it's being produced, kind of.
Yeah, so not capturing it from the water, but actually going down into the rocks themselves and capturing it.
Okay.
This process actually is going on right now in Iceland. So Iceland is on a plate boundary where the European and the North American plates are pulling apart. Hot rocks are coming up to the surface. That's why we have these volcanic eruptions. And the rocks are all cracked up from the tectonics of stretching the crust. There's water circulating through there. Icelanders are using this hot water to produce geothermal heat.
Mm-hmm.
They've also been looking at the water and realized there's a fair amount of hydrogen in it. And they are actually extracting the hydrogen, which is being actively produced at the Mid-Atlantic Ridge under
So you
Iceland.
mean you're going to pipe away the water, so to speak?
Yeah.
Or
So the water comes up, they separate out the hydrogen, and then
like
they
soda pop, like
it's
soda.
like soda pop. They just it's also got some carbon dioxide in it, but they separate out the hydrogen, and then there it is. It's collected.
So if you got hydrogen in Iceland, what are you going to do with it?
Well, they have a very clever solution. Iceland is where a huge amount of bauxite is smelted into aluminum because they have cheap electricity there. And what they've discovered is that they can let the hydrogen be absorbed in the aluminum ingots. And if you heat the ingots, the hydrogen comes out. So they have a perfect serendipity where they've got heat, hydrogen, aluminum, and a transportation mode. So it all works together. It's
like
great.
many other things, works for Iceland, might not work elsewhere. But so moving it around is a problem, though. I mean, if you gather it up, I was saying earlier, I mean, it's not a liquid at room temperature or anywhere close to it. You have to compress it enormously in order to get enough energy into a volume that's transportable. Can we move it around, or does that create a huge problem?
As you know, it's expensive to move around. It is being moved around right now, primarily in the form of fertilizer, ammonia.
Ammonia, yeah.
The optimal thing would be to produce fertilizer locally.
So you pull it out of the ground and then you think, what did we want to use this thing for? Let's have a plant right here that makes fertilizer so that we don't lose half of it in transport or this or that.
It's just another thing that works great in Iceland too, because they could generate electricity from geothermal and use the Haber-Bosch process to convert it into ammonia and ship ammonia instead of aluminum, or maybe along with the aluminum.
They could do that, yeah.
Brad, as you know, I think a lot about developing countries that are economically poor, and in many cases also, and perhaps this is why they're economically poor, also resource poor. The possibility that they have these hydrogen-producing rocks right on their doorsteps, right beneath them, is exciting to me. What about places, for example, in Southeast Asia and in Africa? What's the resource opportunity there?
Yeah, that's great, and it's something I've thought a lot about. So let's start with Southeast Asia. India has a very large deposit of flood basalts. When the dinosaurs were killed 65 million years ago, at the same time, there was a huge volcanic eruption going on over the continent of India, and many people thought that that's what killed the dinosaurs. Anyway, so there's all this 65 million year old iron-rich solidified lava overlying a large portion of India called the Deccan Traps. And that is full of iron.
This is basalt.
It's basalt, yeah. And it's a lot of it is right next to the ocean. So that there's a ready source of water nearby. So that's potential that I would imagine could be low-hanging fruit for the Indians. And then also in India, when India smacked against Asia to form the Tibetan Plateau and the Himalayan mountains, it trapped some very iron-rich rocks in between India and Tibet. So that's another potential source of very iron-rich rocks that the Indians might be able to tap.
What about the rest of Africa? I mean, it's ancient rock, cratons, I think they're called.
Yeah. So Mali is in one of these ancient cratons where these iron-rich rocks are called greenstone belts from some of the fossil plate boundaries back billions of years ago. And also in East Africa, you have the East African Rift, where the crust is pulling apart, bringing iron-rich rocks closer to the surface. There are volcanoes erupting there, so that would be another potential area where you might find hydrogen.
Let me just go back to the Midwest for a second. It sounds like you feel like the venture capitalists, maybe they won't make the kind of money they think they're going to make, or is that wrong?
I don't know if they'll make the kind of money that they think that they will make. There may well be return on investment for the first wave of venture capitalists.
Okay.
But whether this is something which is going to sustain us till 2080, for example.
Right. Will they quickly run through?
Yeah, will they run through and they'll make a killing on their initial investment, but is it sustainable? Is it scalable?
And then another question is, when you talk about this, the thing I think of is like fracking.
Yeah.
Not very far from the kinds of places that you're talking about. A lot of people who live around fracking sites would tell you it's not so great, and there have been a lot of problems. So are a whole new set of people about to come in for the same kinds of problems that the people near the fracking sites have?
Right. So that's a very good question. And I think that's one of the potential obstacles for actively producing hydrogen. I want to be clear, it's not going to be a problem in Kansas where they're just drilling in the same way that we would for natural gas. But if you move to, say, Southern California, there's a spreading plate boundary that comes right up into the Salton Trough area of Southern California. There's geothermal produced there. In many ways, it's an analog to Iceland. It could well be a place where we would produce hydrogen and use it to make fertilizer, et cetera. I think you're going to run into people who are very worried about some of the same problems that fracking produces. Because in order to reach these hot rocks, most places you're going to have to drill down and fracture the rocks to establish permeability.
Are you worried? And what do you think could happen to like ordinary people?
Right. So there are a lot of issues with fracking. One of the main issues of fracking is that a large amount of water has to be injected into the ground. And then once the pumping starts, the fractures close and the water comes out. The surface, this dirty water has to be disposed of. And that's a problem.
Okay.
Stimulation of hydrogen, that is not likely to be an issue because actually what happens is quite a bit of water is absorbed by the rocks in the process of forming the hydrogen. And so you put the water down and it does not come back out. So that's one advantage that it's got over fracking for natural gas. You're going to have an infrastructure to do that. That infrastructure can be messy. And there will be environmental effects associated with it. Probably the major environmental effect is that when you inject water into rock and change the composition of the rock that's down there expands by a substantial fraction. It expands by about 30%. So if you have a zone of rock that you're producing at a depth of 1 kilometer, it's going to cause uplift at the surface. If you're tilting the aqueduct and irrigation ditches in Southern California, people are not going to appreciate that. So you're going to have to be very careful to do this in areas where you're not affecting infrastructure.
What about water consumption itself? I mean, if we're producing something like, well, let's see, today's total consumption of hydrogen is something like 100 megatons globally.
Right.
If we really go big time and find other applications for it, maybe we have a gigaton of hydrogen. Well, okay, so you think about H2O. O has a mass of 16, hydrogen's got 2, so that's 8 times as much mass of water, so 8 gigatons of water. That's a lot of water. Or how is that not a problem if we're producing in the interior of a continent, for example?
Yeah, so the problem is actually worse than that because your rock to hydrogen ratio is not 1-to-1, but it's more like 70-to-1. So you have to react an awful lot of rock and an awful lot of water to produce some hydrogen.
So this is being like injected.
So you're injecting huge amounts of water. So it sounds like an awful lot of water in an area like Superior, Lake Michigan, where you have all these rivers flowing into it. It would not be a problem. It would be a problem in Nevada, for example, if that were there.
So a ton of water is just a cubic meter. So we're talking about 80 billion cubic meters of water a year, which is
80 billion sounds like a lot too. But when you figure out how how
that's a
distributed
tiny
over
fraction of Lake Ontario.
It's not that much water. But one great thing about this is it does not require particularly clean water. So you don't have to use potable water to do it. You could use water from the sea. You could use water from saline aquifers. So you can use cruddy water to do it.
So at what point are we going to be drawing a lot of hydrogen out of the ground, and it's really going to be changing the game in terms of like our energy consumption?
Yeah, you used the word will a second ago. That's intriguing.
Well, maybe I should have used would, but so I'm optimistic about this. So right now there are people who are trying to do this kind of stimulation in Oman. Okay, so Oman is a country in the Middle East. It's right at the mouth of the Persian Gulf where all the oil tankers have to go in and out, and they have a very special geology there. It was an old plate boundary where some iron-rich rocks got thrust up to the surface of the earth, and they're actually exposed. And you can go and look at the outcrops, And you can see this transformation of iron-rich rocks into serpentinite, and you can see that happening, in the outcrop. And there are actually projects which are beginning right now. If those work out, I think that one could begin producing hydrogen in a place like Oman within the next, certainly within the next decade.
And once a lot of hydrogen starts coming out, are people going to immediately know what to do with it? Or are they then going to have that secondary problem of thinking, well, we don't really have a fertilizer plant right next door, and we don't really know how to transport this, so...
Yeah, so that's already a problem that's being worked on in the Mideast. They realize the future of natural gas, with the carbon footprint may be limited, and they're already, investing in things like, fertilizer plants, exporting hydrogen from the Mideast to Japan, for example, using fertilizers. So people are very much aware of that, and these companies are carrying out reasonable techno-economic analyses to see how to do this. So yeah, they're not going into this blind.
So it sounds like in terms of years, we're looking at very soon.
It's
maybe.
wild, right? I
Right?
mean, like in 5 years, we could see a significant amount of hydrogen being produced.
That's my hope. Once it happens, I think people will jump on and you'll get the investments and the technology that you need to really then scale this up to the size that we need.
You mentioned that Breakthrough Energy is investing in some of these companies. And
This
there
is
are
the
a lot
Gates,
of them.
the Bill Gates company.
Yeah, well, Bill
Right.
Gates and others who are putting money into it. Bill,
Yeah, and also philanthropists are going on. The Grantham Foundation has invested in this local company up in Somerville,
exactly.
which is breaking rocks.
Yeah, in Oman.
In Oman,
Right?
they're breaking rocks in Oman. Yeah.
So this is kind of crazy that we've got these philanthropic organizations doing all of the exploration work, and Exxon and Chevron are sitting on the sidelines twiddling their thumbs. I mean, what do we have to do to get them off the sidelines? When does that change? How sure a bet does it have to be? You're willing to invest your meager savings.
Yeah, so I think the oil companies, although they don't want to redirect their research labs to do this, I'm more optimistic than you are, perhaps because I know less about it than you do as in your role in the energy initiative. But I think the oil companies should be investing in the small projects it will take to actually demonstrate the feasibility of this.
So you don't feel like there's some sort of Herculean demonstration that has to be made for them to begin to believe. It's inertia.
I mean, this has only been out, for a few years. It's one thing to have these venture capitalists running around, but if you get, the gravitas of a place like MIT saying we've got this group of a dozen faculty, they really think this is great. And I suppose that's the other thing, is that this is a very multidisciplinary problem, right? You've got to have geologists who know where the rocks are. You have people who understand mechanics, understand rock fracture, how to transport hydrogen through the brines up to the surface, how to stimulate the reactions on the surfaces that are broken. So it's my hope is that by seeing a place like MIT invested in this, and these serious scientists who have many problems they could work on, saying, "Hey, this is the one. Let's do it."
Oil and gas companies are risk averse in many ways. They're making large capital investments, they want them to pay off, but they're also very sensitive to public's reaction to what they're doing. We were talking about environmental concerns a minute ago. Mm-hmm. If we're going to really be producing hydrogen beneath the surface by pumping water down there and fracturing rocks and so on, what sorts of risks do they need to be mindful of? What bad stuff could happen?
Yeah, I think that's a good point, and that's something that we really need to take head on before we run into a situation like it happened with the fracking, methane, and so forth. So just starting in analogy with that. So hydrogen, there will be a certain amount of leakage of hydrogen into the atmosphere. Okay, I mean, that's just unavoidable when you're handling this gas. We've seen the problems that happen with the methane emissions associated with natural gas. So people are right now looking at the implications of additional hydrogen in the atmosphere and what that will do as a greenhouse gas.
What will it do? Nobody talks about. I don't hear people talk about hydrogen as a greenhouse gas. I don't think
it's a new thing. But first of all, I'll say we have hydrogen leaking out all the time.
Right.
So it's already there. So the question is, how much are we going to be leaking compared to the natural flux? But hydrogen by itself is not a greenhouse gas. But there are indirect effects, and I think probably one significant effect, which is easy to understand. When we emit methane into the atmosphere, it decays with a half-life of about 10 years. And that's because it's reacting with, oxygen-containing radicals in the atmosphere. And so if you put hydrogen there, it's going to compete with methane. And so the methane will last longer in the atmosphere.
It won't decay as fast.
It won't decay as fast. So another problem I mentioned previously was just the surface deformation. It's something that happens slowly, gently. You want to make sure your pipes are not altered by it, but it's not a showstopper in my opinion, as long as you avoid critical infrastructure.
Your pipes? What's a pipe?
In your house?
Well, in let's say if you tilted Boston, it would change greatly the flow of sewers into the sewage treatment plant. So that would be a bad idea.
Yes.
Well, and I mean, you see in California these like amazing pictures of how the ground is shifted because the aquifers have been so depleted that people may have a field of rice that's 7 feet lower than it was when their grandfather had that field. I mean, like, really shockingly different, and you can see it in sticks that stick out of the ground or comparisons of pictures from now and 70 years ago or something.
Yeah, there's an amazing picture that the United States Geological Survey puts out for the Great Valley of California, where there's a telephone pole, and they have ground level marked on the telephone pole, and it's down like 80 feet from where it's a whole telephone pole from where it is right now. So
that's just from pumping the aquifers.
That's pumping the aquifers.
Yeah.
But now we're going to be going the other direction.
Now we can jack them up.
Yeah.
Right?
But you have to do it in the same places.
We can jack up Boston Harbor, and so we don't have to worry about MIT being flooded by rising
Oh my
sea level.
gosh, we've solved so many problems.
We can solve a lot of
podcast.
problems by selective uplift around the edges of continent.
Yeah, Brooklyn, we can make Brooklyn a little higher. We could solve, yeah.
I mean, are we going to really be producing enough uplift to be noticeable if we do this?
Oh, absolutely. Yeah, because the amount of rock that's consumed, as I said, you consume like 70 times as much rock as you produce hydrogen. And so, yes, you're creating a lot of uplift.
Probably we won't be doing this in like Brooklyn and Shanghai and stuff, but it seems like a good place to do it.
Yeah, but under the Great Valley is plausible. There are iron-rich rocks under the Great Valley. So
what reassuring words can you give us to prevent the legislatures of the United States from immediately going out and banning hydrogen production?
I think the most fertile place for large-scale, long-term hydrogen production is just on the offshore. So when North America and Europe split apart, the crust got very thin, not very far offshore here. And so we could do this under the water. We know how to do subsurface under ocean. So that's probably where really the big hydrogen production will happen.
So near shore, meaning we still have to build pipelines, but they're not long intercontinental sorts of things. We're just getting it to shore. How far offshore is that?
It's about 100 kilometers offshore.
Okay, so it's like offshore wind almost.
Yeah, a little bit further than offshore wind because it's in the somewhat deeper water. But I think another real serious problem could be the seismicity that's triggered by all this fracturing of rock.
Meaning earthquakes. You just go too far and it lets go.
That seems like a real problem.
Huge amount of deformation. But I believe that can be managed. And one of the most interesting things about this chemical reaction, when you take these kind of hard, brittle rocks and react them with water, and you form rocks like asbestos, which are very kind of soft and squishy, these rocks do not deform in a brittle way. They tend to deform like silly putty, very, very in a ductile way. So there's a place along the San Andreas Fault in California which has almost no earthquakes, and the earthquakes it has is very tiny. And it's a region, 100 or 200 kilometers long that breaks the San Andreas into a northern section where the San Francisco magnitude 8 earthquake happened, and the southern section where a magnitude 8 earthquake happened near Los Angeles. And in between, the plates are just slipping beside each other, just like they're greased. And huge amounts of deformation, larger deformation than we would see associated with production of hydrogen, just happening without seismicity because.
So the ground is getting all changed and looks different.
So the plates are moving. You can go to Central California and go to a curb that crosses the San Andreas Fault, put a paint stripe across the curb, come back in a year and you can see that the curb has been offset.
Wow.
No earthquakes in that time. It's just slowly moving along.
So the big one might never come to.
It will never come to Central California. People are very confident that the big one will never come to Central California.
So do you not worry then that this is potentially induced seismicity is going to be a break on the development of terrestrial hydrogen?
I do worry about that. Because my reasons for believing that it will not be are theoretical and based on analogy to the San Andreas Fault. And I think this needs to be demonstrated in the field. And that there again, that's where this project in Oman could be very, very important because they'll actually be breaking rocks there, injecting, and so we'll be able to, if they monitor that adequately, we ought to get a much better understanding of the earthquake generation associated with this.
So when you just think about like right now in terms of your own career, does this feel like a very exciting time? And does it feel like a pivot point to you? I just wonder in terms of the research you do and the work you follow.
This is a pivotal point. As I mentioned before, this is really an interdisciplinary problem. And, that's something I can do. I understand, kind of the boundaries between geology and geophysics and fluid mechanics and stuff. So for me, it's this new playpen, that just came just at the right time for me that I can, think I can, maybe do one more thing before, and it could be important, if I can make a difference in, the transition to a low carbon economy, that would be very gratifying.
Brad Hager is professor of Earth, Atmospheric, and Planetary Sciences at MIT. Brad, thanks for being here.
Thanks. It's been a pleasure.
Thanks, Brad.
What If It Works is a production of the MIT Energy Initiative. If you like the show, please leave us a review or invite a friend to listen. And remember to subscribe on Apple Podcasts, Spotify, or wherever you get your podcasts. You can find an archive of every episode, all of our show notes, and a lot more at energy.mit.edu/podcasts. And you can learn more about the work of the Energy Initiative and the energy transition at energy.mit.edu. Our original podcast artwork is by Zeitler Design. Special thanks to all of the people at Mighty and MIT who make this show possible. I'm Kara Miller.
And I'm Rob Stoner.
Thanks for listening.